In the last two videos, we took a look at how to get a linear as well as a quadratic polynomial to approximate some sort of value that's not so nice. What we could do is we could be able to use that method that we just saw to be able to find derivatives and then use a formula for an infinite power series. And for our case, it might be finite to be able to get like a third or fifth or even a higher order polynomial to represent a function. And as the degree of the polynomial increases, that means we're going to get a better approximation. So you might recall before that the second order polynomial was represented by this. Now we didn't have 2 factorial, we just had 2. But 2 factorial, remember, is just 2 times 1, which is 2 factorial, which is 2. All right, so this is just another way to write it. If we continue that pattern, and remember before that we were able to solve for the coefficients like C3, C4, C2 by taking the derivatives and setting them equal, we would eventually get this formula where all we have to do is just keep taking the derivatives or the nth degree derivative. So when you see this notation, that just means the nth derivative at A. Okay, so that's the nth derivative. All right, and then evaluated A, and then we have n factorial, okay? Or another way to write that is centered about a value A is to use this Taylor polynomials or Taylor series, okay? So this is a Taylor series, and this is a Taylor polynomial. All right. And again, if you wanted to try to derive this, you very easily could do it by using the finding C3, C4, C5, just like we did in the second video in the series. All right, so I'm going to show you 2 polynomials to find 2 Taylor polynomials for P1, P2, P3, P4, and P5. Okay, so let's take a look at this function, sine of 2x. Centered about a equals 0. And let's see if we can find a polynomial to represent sine of 2x about a equals 0. And then I'll show you what happens as the degree of the polynomial increases by graphing them on some sort of graphing device together. All right, so because we need a 5th degree polynomial, what we're going to do is we're going to find 5 derivatives. Okay, so we know that, and we're going to use n to be the order of the derivative. Okay, so I'm going to make a table out of this. So n is going to be 0, 1, 2, 3, 4, and 5. Okay, and that's because I have to go up to P5. Then I'm going to find f prime or fn of x, the nth derivative of that. So this is going to be fn of x. Then I'm going to find fn at a, okay, which is going to be the derivative at a. All right, so the 0th derivative is always just the original function. Okay, so that's going to be sine of 2x. Okay, so the function itself is always going to be the 0th derivative. Each time we find the derivative, we're going to use the chain rule. So the first derivative is going to be 2 cosine of 2x. The second derivative is going to be -4 sine of 2x. And remember, when you take the derivative of cosine, you get a negative sign, right? And then third derivative is going to be -8 cosine of 2x. The fourth derivative is going to be +16 sine of 2x. And then finally, this is going to be 32 cosine of 2x. Now we're going to substitute 0 back in, okay, because remember we said centered at a equals 0, right? So this is going to be sine of 2 times 0, which is just going to be 0. This is 2 cos of 2 times 0, which is going to be 2 times 1, which is 2. This is going to be -4 sine of 2 times 0, which is 0. And then anytime we have a sign of 0, it's going to be 0. So this will be 16 sine 2 times 0, which is going to be 0 as well, right? And then anytime we have a cosine, that's going to work out to be 1. So we have minus 8 cos 2 times 0, which is negative 8. And then finally, 32 cos 2 times 0, which is 32. All right, so now we can go ahead and try to find the various polynomials for this. All right, so remember, we're going to use this formula. Okay, so for P, and I'm going to write them out since it's the first time that we've seen this. Okay, so now P sub 1 of x, right? And if we're looking at our formula, that's just going to be f at a, f prime at a, x minus a. All right, so that's actually just our linear sort of thing. So we have f at a is 0 plus f prime of a, which is 2, x minus 0, okay? Or in other words, that's just 2x, okay? For P2, that's going to be 0 plus 2x minus 0 plus, and then we're going to take the second derivative right here. That's going to be 0 over 2 factorial x minus 0 squared. And again, that goes away, and we're left with 2x, right? P3. And each time we find a next order polynomial, we're just recycling the previous terms. So 0 plus 2 x minus 0 plus 0 over 2 factorial x minus 0 squared. And now we're going to take the third derivative at a. So that's going to be plus negative 8 over 3 factorial x minus 0 cubed. Okay. Now we know 3 factorial is 6. So when we simplify this for P3, that's going to be 2x minus 8 over 6 x cubed. Okay. Or 4/3 if we were to go through and simplify a little bit more. Right. So that's going to be 4/3. So we're going to hold on to these, okay, because these are going to be our polynomials, right? And you might be wondering, okay, well, that's a second order sort of polynomial. Remember, there's a 0x squaring here, okay? So that's the coefficient of the x squared term. So technically, even though there's no square, it's really a 0x squaring. Okay? That's actually going to happen for P4 as well. So P4 of x is going to be precisely what we just had. Okay, so that's going to be 0 plus 2x minus 0 plus 0 over 2 factorial x minus 0 cubed plus 8 over 3 factorial x minus 0, or x minus 0 squared, excuse me. And this is x minus 0 cubed. All right, and then finally, we're going to go back up to the fourth derivative, which was 0. And that's going to be plus 0 over 4 factorial x minus 0 to the 4th. Now this goes away, this goes away, this goes away because the zeros. All right. And what we're left with is 2x plus 4/3 x cubed. Okay, so same thing, or 2/3 minus, excuse me, because remember it was negative. All right, so I think I made a sign error when copying this. All right, so this is a minus. Right, and so we have an x cubed here, all right, and then a minus here. All right, so it looks like P4 is the same as P5, and that's okay. Right? And then finally, we get to P5, and we can use this fifth derivative, which is going to be 32. All right, so P5 of x is going to be exactly the same as what we just had. So 0 plus 2x minus 0 plus 0 over 2 fact x minus 0 squared minus 8 over 3 fact x minus 0 cubed plus 0 over 4 fact x minus 0 to the 4th, and then plus 32 over 5 factorial x minus 0 to the 5th. All right, so terms go away. we're going to copy down 2x minus 4/3 x cubed, and then 32 over 5 factorial. We could just simplify that by looking at it in the calculator. So that's going to be 32 divided by 1 times 2 times 3 times 4 times 5, which is 120. All right, and then we can just use the fraction, and that's 4/15. Okay, so that's going to be plus 4/15 x to the 5th. Okay, so that's our P5. All right. Now, one last thing that I want to do before we conclude this, because again, all I asked you to do was to find the the Taylor polynomials for this. Let's graph these on the same graph as the original function, which was sine of 2x. All right, so I'm going to go ahead and just pull up Desmos and graphing calculator. Right? And let's just see what happens. Okay, so remember, our original function was sine of 2x. Okay, going all the way back here. All right, and we're really looking at what happens around the origin for this. Okay, so I'm going to zoom in just a little bit. Okay, because again, I'm only interested around what happens around the origin. Okay, as we keep getting further from the origin, then we're probably going to stray a little bit. Okay, so remember, one function we had was 2x. So let's plot 2x and see what happens. Okay, and if I plot 2x, it's not really all, oh, that's 21x. So 2x is not a bad interpolation, okay, or approximation, at least like maybe to like right about here, okay, like about 0.4 or something like that. Now, the next one we had was 2x minus 4/3 x cubed. All right. Now notice that this is a much better fit, okay, to about 0.707, and then it starts to diverge just a little bit from the behavior, but it's still not all that bad. Right? Now remember, the last one we had was 2x minus 4/3 x cubed, and then we plus, I think it was 4/15 x to the 5th. All right. Now notice how good this is. And I want you to notice that as we increase the degree of the Taylor polynomial, especially around the origin, we seem to get a better and better approximation. And that's why we want to keep increasing the order of these Taylor polynomials, is because we keep getting better and better approximations around the point a equals 0. Okay, so we'll see this again in another problem. But for right now, all we're interested in is being able to get these various polynomials, the Taylor polynomials, for these sorts of functions that might not be so nice for us to deal with.